Welcome all to the video on crystallizer types and application and also the design of a crystallizer. I am Dr. G. Kirtika, Associate Professor of Chemical Engineering, SRM-ISD. Coming to the crystallizer definition, it is an equipment used to produce solid crystals from a liquid solution or melt by creating supersaturation. The purpose of the crystallizer is to achieve desired crystalline size, purity, yield and the product production rate. So here we can see from the liquid. So we concentrate the liquid and when the liquid attains supersaturations, nucleation proceeds and from which the crystal is formed. Once the crystal is formed, the crystal grows and attain the desired product. Coming to the application, this crystallizer has been used in numerous applications and it is not limited to these applications. Preferably, it is used in sugar industries for manufacturing sugar, salt, in the salt production. In the fertilizer industries, it is used for urea and ammonium sulfate production. In pharmaceutical industries, it is preferably used for purification of the drugs, in fine chemicals, in food process industries, and also in recovery of metals and inorganic salts in the organic industries. Next, moving to the advantage of crystallization, it helps in producing high pure products. It helps in recovery through separation and further purification. It produces solid products directly. Mechanism of crystallization, there are two important mechanisms which has to be discussed. One is nucleation, the other one is crystal growth. So what is nucleation? Nucleation is a formation of tiny stable crystals from a supersaturated solution. So once the nucleation begins, with respect to time, it decreases and the crystal growth occurs. The crystal formation tends to begin as the nucleation is formed and the crystal rate of the crystal growth increases with time. Here in nucleation, there are two types. One is primary nucleation, the other one is secondary nucleation. In primary nucleation, there is no existing crystals. Means by supersaturation only the nuclei are being formed. But in secondary nucleation, we intentionally add some crystals to initiate the nucleation process and the crystal growth. So this is a primary difference between the nucleation types. Coming to the types of crystallizer, there are different types which is mentioned in different books, textbooks and also videos. This is one such classification where it is classified based on the functions like batch and continuous. In batch, it is suitable for small scale production, and in continuous you can have mixed suspension, mixed product removal crystallizer. It is a continuous crystallizer and it produces uniform crystals. In forced circulation crystallizer is used for high viscous and fouling solution because we have a pump to ensure the slurry is moving into the main body of the crystallizer and we have a high circulation rate. In draft tube baffle crystallizer, it produces large quantity of crystals and it has internal crystal classifications. Classification based on supersaturation. So based on the method of supersaturation, the crystallizer can be classified as supersaturation by cooling. So when you cool the magma, the supersaturation occurs from which the crystallization begins. It is classified as batch and continuous. In batch, you have agitated tank crystallizer and in continuous, you have Swenson-Walker crystallizer. Next is supersaturation by adiabatic evaporation and cooling. So here it mainly occurs in vacuum crystallizer. So in here since the pressure drop is reduced, here the temperature of crystallization or temperature of supersaturation is reduced so that the supersaturation occurs, nuclei forms and the crystal growth occurs. Next is supersaturation by evaporation. Here we have a continuous crystallizer like crystal crystallizer and also draft tube crystallizer. So now we will see a crystal crystallizer and its working, like by evaporation. How does this crystallizer works? And here let us discuss crystal crystallizer, which is an example of forced circulation evaporative crystallizer. Here the feed enters through the circulating pipe, and through the pump the feed is fed into the heat exchanger. In the heat exchanger, the temperature of the slurry is increased by 2 to 6 degrees Celsius. After which, no, there is no boiling occurs, only there is a sensible heat transfer occurs, and from here, the solution is forced into the main body of the crystallizer. So here since it is heated, supersaturation begins to occur, and whatever liquid like whatever water is evaporated, it is removed by the condenser. So there is a continuous vapor removal through the condenser, and the concentration occurs in the evaporator, and also by which the solution is cooled. So here we have the nucleation process, and once the nucleation begins, the crystal formation also occurs. Here the product is withdrawn when the product is returned through a circulating pipe at a little higher level than the feed inlet. So there is a continuous mechanism of crystal production in this post circulation evaporative crystallizer. Yes. So next we move on to solving a crystallizer problem. So here we will estimate the cooling water which is required and number of crystallizer section which is required to achieve the desired crystal formation. So to discuss this question, it has 2000 kg per hour of iron sulfate crystals are produced in a Swenson-Walker crystallizer by cooling a saturated solution from 50 to 80 degrees. Cooling water enters the jacket at 15 degrees and leaves at 20 degrees. The overall heat transfer coefficient U is 180 kilocalorie per hour meter square degree Celsius and or 3 square meters of cooling surface per meter length. So now what is given in the problem? The problem gives the crystal, like flow rate of crystal, the temperature of the feed as 50 and temperature of the product is at 18. The water enters and it removes, it helps in cooling, which enters at 15 and leaves at 20. So some more data is also shared in the problem. A saturated solution of ferrous sulfate has 140 parts and 74 parts of iron sulfate per 100 parts of water at 50 and 18 degrees respectively. So this gives the solubility data. So at 50 degree, the solubility is 140 parts of iron sulfate per 140 per iron sulfate molecule plus water, 100 parts of water. Similarly, 74 parts which is present in total iron sulfate plus 100 parts of water. Cp is given and lambda values is given for heat transfer. So now how do we solve this problem? We can first do a mass balance. We'll find the solubility, and from there we will find the composition of crystal, composition of the mother liquor, composition of the feed. We will do a material balance on both sides, and from there we will find the feed flow rate, mother liquid flow rate, and also the crystal flow rate. We will do an energy balance to find the area of the crystallizer, and we also do how many sections are required for solving this problem. So coming to the molecular weight, we have to estimate the molecular weight of iron sulfate. So we know iron has 56, sulfur 32 and oxygen 16, from which the molecular weight of crystal. So the 7H2O indicates a complete iron sulfate crystal, and FeSO4 indicates it is in the solution form along with water. Right? So the molecular weight is determined. It helps in finding the solubility data. So here we have to find the solubility of the iron sulfate at 50, which will give you the feed composition, and also at 18 will give you the mother liquor composition. So here at 50 degrees, it is given 140 parts of iron sulfate in 100 parts of water. So multiply 140 to individual molecular weight by total molecular weight of iron sulfate crystal. That is 152 divided by 278 into 140 will give you solubility at 50 degrees Celsius. So do the same thing for mother liquor. 74 parts into individual molecular weight of iron sulfate divided by the total molecular weight of iron sulfate crystal, that is FeSO4.7H2O. So with these solubility values, we further compute the crystal composition. So here for crystal formation, it is just molecular weight of individual iron sulfate to the molecular weight of iron sulfate dot 7H2O. This gives us a crystal composition, and for feed solution composition, we have to divide the individual divided by total. So 76 parts is present in 76 plus 100 parts of water. So 76 indicates the solubility of at 50 degrees, the solubility of iron sulfate at 50 degrees in the feed, divided by total quantity which is present in the solution, which is 100 parts of water plus 76.55 parts of iron sulfate. So this will give you the composition of feed, which is 0.43. Similarly, do for mother liquor. The solubility at 18 degrees, which is calculated in the previous step, divided by total solubility of with water. So total iron sulfate crystal present in the mother liquor is 40 plus 100. This will give you the composition of the mother liquor. So these compositions are required, or the first step is calculation of this composition for doing a mass balance. So here the important thing is we should know the molecular weights, and also we should know how many number of crystal water molecules are required for crystal formation. Coming to the material balance, we have two equations. One is overall material balance, the other one is solute balance. So overall material balance, feed enters and it is produced as mother liquor plus crystals. Anyway, solvent is evaporated and solvent is only water. So we need not account for evaporative solvent in the material balance. And coming to the solute balance, we have MXF plus FXF plus MXM plus C into XC, because everywhere we have iron sulfate which is present. So here we know the composition XF, we know composition XM, and also we know composition XC. The other data which is given in the question is flow rate of crystals. So flow rate of crystal is 2000 kg per hour. That can be substituted here. So here instead of M can be written as F minus C. So F minus C is F minus 2000. The only unknown here is F. So yeah, it can be solved for F, and the feed flow rate can be computed as 3548 kg per hour. So once you substitute this F, you can also find M, the flow rate of mother liquor. So moving to the heat balance. So it's also known as energy balance. So how much energy, input energy, which is given to the crystallizer, that is equal to, that is required to rise the sensible heat and also the latent heat. So here it has two parts. So one is mCp delta T, the other one is m into lambda. Fine. So you know F from the previous material balance step. So substitute for Cp which is given. This is a Cp of the solution, and the temperature difference in the feed is from 50 to 18 degrees Celsius. So C is flow rate of crystals, and the crystals carries the latent heat, and the lambda of the latent heat of solution is also given. So from which the total heat removed in the crystallizer will be estimated as 231075 kilocalories per hour. So coming to the temperature profile, we know cooling water is used for removing the heat, and the feed solution is cooled from 50 to 18 degrees Celsius. So here it occurs in a counter current manner. So you can use LMT, you can use LMTD for counter current. and you can find the LMTD values. So it is inlet minus outlet of inlet of feed minus outlet of water, and outlet of feed minus inlet of water. That's what has been substituted. So you find 50 minus 20 minus of 18 minus 50 and divided by the consecutive ln values to get logarithmic temperature difference. So here we have calculated Q and also delta T. So why we are doing this? Because we need to find the cooling water rate. So how much water cooling water enters to achieve the desired cooling. So the cooling water requirement can be calculated as Q is equal to mCp delta T of cooling water. So Cp is water. So the Cp of the water can be taken as 1 kilocalories per kg degree Celsius, and delta T is temperature difference of water. So the water rises by 5 degrees in the process of evaporation, and Q is the heat which is removed by the crystallizer. So heat removed by the crystallizer from the previous step is taken, and the cooling water rate is estimated as 46,215 kgs per hour. So this is the first question which is asked. Estimate the cooling water required to achieve desired crystallization process. Second is to find the area of the crystallizer. Here again we go to the Q is equal to UA delta T, where you can find the area. Here delta T is logarithmic temperature difference, and Q is heat which is removed by the crystallizer, and U is overall heat transfer coefficient. Here U is given in the question, and Q we computed. Logarithmic delta temperature, mean temperature is also known, and hence you can find the area. Here area 109.44 is the total area which is required by the crystallizer to achieve the desired purity or separation. But we have each section of 3.5 meter long and 3 square meters of cooling surface per meter length. So we have to find we have to divide this 109 into number of crystallizer sections, where each crystallizer should be 3.5 meter long and it should have a square meters of 3 square meters. If that is the case, so the area of each section will be 3.5 into 3 square meters, which is 10.5 meters squared. So we should have one crystallizer of 10.5 meters squared. Then how many such crystallizer could be required to achieve an area of 109.44 meters squared? So you just divide 109 by individual area of the crystallizer, you will get approximately 11 sections. So to achieve the desired crystallization process, 11 sections of the crystallizer, each of 3.5 meter long and each of 3 square meters, has to be placed to achieve the desired crystal formation. Okay, so this is the second portion of the problem. So we have estimated some of the design parameters like area, number of sections, and also the cooling water rate. So the reference of this crystallization problem is from Coulson and Richardson volume 6, and theory is from NPTEL course of process equipment design developed by IIT K. So I also thank you for listening to this video, and please post your comments and questions. Thank you so much.